Okay, so over to George Seabroke, who's going to talk about the radial velocity work.
Yeah, well, thank you very much for the opportunity to speak. We've heard from Francesca about the Gaia DR2 revolution in astrometry and photometry, and also in radial velocity. So along with Mark Cropper, I'll be talking about giving you some more details on the revolution in radial velocities. So the radial velocities with Gaia are measured with the radial velocity spectrometer. So as Gaia is spinning, the sky drifts across the focal plane here, so just on the ground here. And so the sky passes through, and as it passes through the RVS, the 12 CCDs here, the light passes through all of these optics here, which disperses the light and gives us our RVS spectrum. So Mark Cropper's paper here describes the RVS instrument, the design and the implementation and the commissioning. So the on-ground processing is described in this schematic here. All the gory details of the spectroscopic pipeline are in this paper here. I won't go through the details, but just to say that MSSL is a major contributor to the scientific modules that make up this pipeline here, and to give you some idea, as all these boxes are equally sized, that MSSL are responsible for the work packages of calibration, preparation, calibration, full extraction, and the multi-transit analysis here. So the biggest box here is calibration, as that's the most code and the most complexity going into Gaia DR2. So the RVS spectra that were processed in Gaia DR2, the selection was based on an unpublished GRVS magnitude. So this is its relation to the Gaia G magnitude, which you'll be more familiar with here. So we selected spectra brighter than this limit. So that equates to 280 million spectra that were processed in preparation for Gaia DR2. And of course, you've heard about the number of radial velocities from Francesca. That was 7.2 million stars provided with radial velocities in Gaia DR2. So the processing takes the raw spectra here. So this is in counts against sample number here. And so the calibration that takes place derives the calibration coefficients required to correct this bias non-uniformity here. This step here is happening at a boundary here which needs to be corrected, and that bias non-uniformity is corrected in the extraction of the spectra. And here we have a normalized wavelength calibrated spectrum. So this example is 11th magnitude, so you can just about see the calcium triplet lines here. And the spectrum's been cut between these two wavelengths here. And just to give you a bit of flavour of what the spectral glass is capable of the brighter end. So G of 8, you can see the calcium lines much clearer, and you can also see some weaker lines. So in this diagram here, the iron and silicon lines have been labelled. So the validation of all the radial velocities that were published are in this paper here. So the plots that Francesca showed are from this paper. So the stars which have radial velocities in Gaia DR2 are shown in here. So this is the G histogram, the G magnitude histogram of those stars, and it's peaking between the G of about 12 and 13. So this is showing all of those 7.2 million stars on the sky, according to density on the heel pix position in the sky here. So you can see that, as expected, we're most dense towards the galactic plane. So we have the highest number of stars with radial velocities towards the galactic plane. But it's also towards the galactic plane that we have the least completeness. So the completeness goes down to 25% in this diagram here, close to the galactic plane, in fact, in the galactic center, and increases up to getting closer to 100% away from the galactic plane. And that completeness here, as a function of G magnitude, is shown in this plot. So we're reaching nearly 80% at G of 11.75. So this slide is showing the 6 numbers that the spectroscopic pipeline were providing for Gaia DR2. So radial velocity error. So the data model describing DR2 was set up a long time ago, before many members in Gaia realised that in actual fact it should be radial velocity uncertainty. So this is not an error in the true sense, but an uncertainty. So this is the radial velocity precision. And then also the number of transits. And then we provide the stellar atmospheric parameters of the template which was used to derive the radial velocity. So as Francesca mentioned, we limit our stars between this temperature range, and this is because we'll be using atmospheric parameters from Gaia data themselves. But for Gaia DR2, we needed to use a combination of ground-based knowledge or deriving the parameters ourselves. So due to processing time constraints, the library from which we used the templates was necessarily small. And so we found in deriving which template we should be using outside of this region, we found that we're having a template mismatch which caused radial velocity biases which are unacceptable for publication. And so this will be improved in future data releases as we use the atmospheric parameters coming from the Gaia data and the BP and RP spectra which you heard about earlier. So this is a histogram of all 7.2 million radial velocities in Gaia DR2. So it's a log plot on the Y scale. So you'll see the limits here that our search region for deriving radial velocities is between plus or minus 1,000 kilometers per second. So we provide the median radial velocity over a number of transits. So the radial velocity of each transit, of each scan of the sky, is derived, and the value in the Gaia DR2 archive is the median of these. So this is a histogram of the number of transits of the stars for which we measure radial velocities, with the median being at about 7 here. So you may have spotted some features in this histogram. So in particular, this one got me excited initially, thinking, oh, this could be a new stellar stream. But it is actually the low galactic latitude globular cluster NGC 3201. Also, this little peak here is the Large Magellanic Cloud. And the highest radial velocity of the high velocity stars in this paper here is this one here at minus 614 kilometers per second. So this isn't the fastest of the high velocity stars in this particular paper, but it is going at a fair whack at 747 kilometers per second in that galactic rest frame. So here is the distribution of the radial velocity uncertainty. There's a cut here at 20 kilometers per second, and you can see that we're strongly peaked at less than 1 kilometer per second precision. So the extended tail includes a mixture of stars with insufficient signal, so this could be the wrong magnitude, and also undetected large amplitude variables, undetected binary or multiple systems, and undetected emission line spectra. So where we have detected these sorts of systems, we've excluded them because we don't yet have templates with which to derive the radial velocity for these stars, but this will be improved in the future. And also, when we detect these in future data releases, we will model them, we will identify them and model them appropriately to provide the best radial velocity for these different types of stars. So you'll all be familiar with Gaia DR2's all-color, all-sky, two-color map here based on the BP and RP photometry, which Francesca told you about. So I'm now overlaying the radial velocity map, just to give you your bearings. So you can see here that this all-sky radial velocity map, that you see the Large Magellanic Cloud, which you saw in the previous plot, and the Small Magellanic Cloud here. And then this is the map without the transparency to give you your bearings. So if I just flip between those. So this is being ably demonstrated by my beautiful assistant here. In case you were wondering what this was doing, it's not the CMB. This is the radial velocities from Gaia DR2. So if you'd like to have a play with this, please come and speak to me. It's not a touchscreen sphere, so please don't touch it. But I'll come and show you about it in breaks or at lunchtime. So As Francesca said, this is the first all-sky radial velocity map. So all 7.2 million stars are in there, and the blue indicates stars moving towards us, and red moving away, as you might think. So the pattern is the line of sight projected differential rotation of stars in the galaxy as seen from the sun. So it's demonstrating Ort's constant. So the power of the radial velocities is really in combining them with Gaia DR2 proper motions and parallaxes to get the 3D space velocities. So here is the V-phi, the galactic cylindrical azimuthal velocity plotted here against the other two, so the radial and the vertical one here. And this was done in the science demonstration paper here, mapping the Milky Way disk kinematics. So this is a Toomre diagram with a log star density here, just to illustrate that basically the circular velocity on the x-axis here and random velocity on the y shows that the sample, this 6D phase sample, is dominated by thin disk stars. But we can also see the asymmetry here with the thick disk and halo stars as well. This 6D sample from this paper is now plotted in the HR diagram here. So there's 4 million stars with three-dimensional velocities in this diagram. So absolute magnitude in G, so similar to what Francesca was showing in her talk against the BPRP color. So if we select the giants here, just to give you an indication of the volume that the 6D sample is sampling within the galaxy. This plot here is from the paper here, showing in X and Y. We're showing the galactic cylindrical radial velocity in this case, so positive towards the galactic center. So the galactic center is along here, with the sun here. So we'd expect this plot to be this particular velocity to be 0 if the galaxy was in equilibrium. As you can see, it most certainly is not in equilibrium. And there have been a lot of papers looking at this. In particular, Daisuke Kurata will be talking about this sort of thing a bit later. But just to say that there seems to be streaming motions here, in that we have stars moving towards the galactic center here and then away here. So we seem to have a negative gradient. And so the streaming motion here is producing a lot of good science, which I think we might hear about later. So just to summarize, so Gaia DR2 contains the largest radial velocity catalogue to date. 7.2 million stars with radial velocities, so nominally brighter than GRVS of 12th magnitude. I haven't shown you here, but the details in the paper here, that the radial velocity uncertainty is a function of many things: stellar type, the number of transits, sky position, the level of detected emission, and RV variability, and many other things. So the details, as I say, are in this paper here. The atmospheric parameters of the templates have been published in Gaia DR2 for reference. You shouldn't use those for science. And there's no RVS spectra in Gaia DR2. But looking forward to Gaia DR3, it should increase the completeness and reduce the radial velocity uncertainties of the Gaia DR2 stars, as well as push fainter with a wider effective temperature range. So we're going to go fainter to GRVS of 14th magnitude. So this could be up to 30 million stars. For a subset of these, we'll be providing rotational velocities in addition to the radial velocities. And RVS spectra will be published for the first time for a subset of these stars, for which the following has been derived. And this is all still being discussed internally. But atmospheric parameters, as you'd expect, 5 individual abundances and a diffuse interstellar band estimation. So as this, I look forward to Gaia DR3 is showing the revolution is really only just beginning. So thank you.
Phil Charles, Southampton. Your radial velocity distribution did have a handful of stars with extremely high velocities, way above the things you were explaining. Are they? I know they're not very many, but are they interesting objects that should be followed up, runaways or whatever?
So I think yeah, various people are following them up. So there are. I just picked out the one that had the highest radial velocity in that particular paper. I know other people are following them up. As described in the David Katz paper, the validation paper. All stars above plus or minus 500 kilometers per second radial velocity have had their spectra eyeballed to check. So that's really only a handful, as you've seen, to check that they are so that they're real. So as far as we can tell from the spectrum, they appear to be real. But I know various people are following them up. So I guess you've got to keep an eye on the literature, I guess is the answer.